push that rock here with some math. Sick 'em bears. So we need to do an example of a definite integral where it's necessary to do u-substitution. And you can tell by the fact that I have these graphs drawn here that there's some kind of technicality. So the u-sub we went over last time is quite easy here. We're going to let u be the function that we think is an antiderivative of some other function. Well, to see it, maybe I should rewrite this a little bit. I'm going to change this to the natural log of x times 1 over x with respect to x. So we see the two functions. So if I let u be the natural log of x, then the differential of u is the derivative of this times dx, and the derivative of this is vanishing log rule 1 over x, and then it's times dx because we want the differential of u. So it's the derivative times the differential of x. Now notice I have 1 over x dx is just du, so I can replace the 1 over x dx with the du. That's nice. And then we let u be natural log of x all along, so this is u. So that's nice. But we have a problem here. I cannot just willy-nilly write down a 1 here and an e here. That wouldn't make any sense. Let me explain why. Right here I have a graph of this integrand. Y equals the natural log of x over x from the interval 1 to e. E's a little bit shy of 3. Well, there's this nice little pseudo triangle. It's a pseudo because that's a curve, but it looks like a triangle. But it's got a curved side. And it's a small little area. I mean, look, this is a width of less than 3 and a height of 1, so it's way less than 1 by 3, okay? So it's way less than 3 square units. It's way smaller than that because we're leaving out all this area over here. We're leaving out a significant area here. So it's a small little tiny area. Now look, if I put 1 and e here, then that means I'm looking at the area under this line. This is just the line, y equals u. That's like y equals x, only we've changed the input variable to the dummy variable. And we're looking at it by 1 by 8. So that would be a trapezoid here. And it'd be a fairly large one. Look, if you put in e into this function, you go all the way up to e. So this is a large area. It's way bigger than that area, so these would not be equal. So I cannot say that this equals this if I put the same limits of integration. Clearly that would be wrong. So how do I adjust? Well, remember we have a relationship between u and x. We have a function. U is a function of x. So u is equal to the natural log of x. And these are x values. See, they're on the x-axis 1 and e. So if I want to know u at e, I put e in here and I get the natural log of e, and so u of e is 1. So this e, when we switch to u-talk, corresponds to 1. What about at 1? Well, it's the same thing. If I want to know u of 1, I put in 1 for the x, and I get the natural log of 1, which of course we all know is 0. So this 1, when we switch to u-talk, corresponds to 0. Now let's look at the area under this curve now from 0 to 1. See, from 0 to 1, look, we have this nice little perfect triangle. And it looks like this triangle might have the same area as this little area here. This actually looks a little bigger, but you know, I was just sketching this roughly. So I probably exaggerated the y value some. So this has a much more realistic chance of being this area. And in fact, because I did this properly, this area is the same as that area. So I can say that this definite integral equals this definite integral. So now I'm ready to integrate. Well, when we integrate a line, you get a parabola. You add 1 to the exponent, get a 2, and then you put the reciprocal out front, and we're doing a definite integral, so don't forget that you need these limits of integration. We need to evaluate the function at 1, so I get 1/2 of 1 squared minus 1/2 of 0 squared that's just 0, and 1 squared is 1, so I just get 1/2. And so this area is 1/2 square unit. And the value of this definite integral from 1 to e of the natural log of x divided by x with respect to x is 1/2. Math made simple. That's Simpson math.